Alright, looking at number 31 now. An advertisement for a toy ball once stated that it would rebound to a greater height than the height from which it was dropped. Is this possible? No, that's voodoo. The only way you would be able to make it rebound higher would be if it is given additional energy for that to work. The energy has to be conserved, therefore the starting energy has to be equal to the the final energy. So when you drop the ball, it has a certain amount of potential energy. As it falls, that changes into kinetic. That kinetic also gets converted into spring, and then back into kinetic, and then back into gravitational potential. Throughout that whole process, it's the same amount of energy. It can't bounce any higher unless you somehow added energy into it. So they were lying. Don't believe advertisements. 33 then. A child in a sled with a combined mass of 50 kilograms slide down a hill 7.34 meters high. Starts from rest. What's the speed at the bottom of the hill? Well, they're saying it's a frictionless hill, and they're saying that you're starting off at a given height. Remember when we talked about the whole conversion of energy thing, and the mass is irrelevant. So 2gh, 7.34 meters. Vi is 0. Find Vf. Just use that formula. Put in your h. And it comes out to be... where's that at? Somewhere in the 10 meter per second range. 34, the Tarzan question. Tarzan swings on a 30-meter rope, or vine, initially inclined at an angle 37 degrees with vertical. What is his speed at the bottom of the swing if he does the following, from rest and initial speed? Well, the big idea in this question is figuring out the height, and once we know height, we can say Vi is either 0 for part A or 4 for part B, and calculate Vf. But we got to get that height first, so let's draw ourselves a little swing here. So there's Tarzan's vine at an incline of 37 degrees. Okay, let's see if I can draw a nice little angle. Yeah, that's not working for me. Yeah, excuse me on that one. It's just not working out to my liking. Rotate, no, just rotate this one. Sometimes I have to fight with my shapes. Okay, so the trick on this one really is getting the height. And the height is going to be represented by this here. That's the height we need to find. Well, we're going to use triangles that we know. We know this is 30 meters. We know this is 30 meters. We're going to draw a horizontal line here. If we know this is 30 meters, we know this is 37 degrees. We can then calculate this length here. And while I don't have the calculator running in front of me, I'm willing to bet it's like 2/3 the length. So let's just estimate. Let's what if and say this was 20 meters. If this is 30, if this is 30, and this is here in red is 20, that would leave a height of 10 meters. So then you plug in your 10 meters into here. 10 meters, 2gh. Vi would be 0 for part A. Calculate the final velocity. Then for part B, his initial velocity is 4. You just put that in. Then you calculate final velocity again. And you get answers in the 10 meter per second range when you're calculating those. So the big idea there is going to be getting that height. This is just like that swing problem we did for homework. And then number 35. If an automobile engine delivers 50 horsepower of power, how much work will it take, or how much time will it take for the engine to do so many joules of work? 6.4 times 10 to the 5th joules of work. Well, so now we're into power here. And we've got power, we've got work, we've got time. So we're going to use the first equation. You do have to convert the horsepower into watts. So you're going to take the 50 horses times the 746 watts listed in the problem, and you'll get, I don't know, whatever that is, times 50. So that'll give you the power. Then you've got the work at 640,000 joules. And then you just divide and find time. Or multiply. Whatever. You solve it for time. For 35.